Now let us try to find out the phase noise in the LC cross-coupled VCO. LC cross-coupled VCO. So let us draw the equivalent circuit. So this is the inductor. And for this phase noise analysis, you can model the entire output capacitance as a single capacitor like this. And the loss present in the tank, let's model it as a parallel resistance RP. And this circuit is connected to a cross-coupled MOS to compensate the loss. With a tail current. So if we look at this circuit, we can see that the noise is going to be generated by this RP, by these two transconductors, and by the circuit which will be used for this bias current. First, we will focus on the noise due to this RP and these transconductors. So RP is adding current noise in parallel. These two transconductors also adding some current noise. So this is 4 kT by RP. So this current noise, let's say, has PSD of we have already done the analysis earlier that if we are looking at the output noise voltage at a offset delta omega from the resonance frequency of this LC tank, then this LC tank starts looking like just either capacitor or inductor. So if the offset is higher than the omega naught, then this LC tank looks like just a capacitor or equivalent value 2C. So to find the noise voltage due to this current noise, we can just multiply this current source with the output impedance to get the output voltage noise. Here we are considering RP is completely cancelled by the negative resistance offered by the cross-coupled pair. Now, if you look at the noise from these transconductors, then as we discussed earlier, that because of this large signal swing, the GM of these transconductors will also change. So, if we have to plot this GM versus time, so it may look like this. And it is going to be periodic. So this is happening because we have got large voltage swing at the output. So if you remember, we talked about an effective GM, which was the ratio of the fundamental current supplied by the GM with respect to the fundamental voltage which is applied at the gate of these transistors. So the effective GM value will be somewhere in between these two extremes in which the GM is swinging. So we can talk about some GM effective Let's call it GM0. And we will say that the noise generated by this transconductors is also decided by this effective GM rather than the instantaneous value of this GM. So under this simplification, we are going to find out what is going to be the output voltage noise in this VCO. So if we call V0 as the net output voltage, then the output voltage noise PSD we can write as composed of contribution due to all these three sources. So due to the RP, this current will just multiply with the effective tank impedance. So this noise PSD we can define at a delta omega offset from the resonance frequency to be equal to 4 kT by RP, that is the current noise, multiplied by the effective tank impedance, which is 1 by delta omega C, and then we will take a square of this impedance. Plus, we need to find the contribution from the transconductor noise. The transfer function from this current source to the output voltage will again involve multiplication with the equivalent tank impedance, but the effective differential current is going to be only half of this current source. So the contribution from the GM is going to be 4 kT gamma GM0, that is the effective GM, multiplied by half, then the tank effective impedance, which is 1 by 2 delta omega C, then overall square. We can see that the same transfer function we can also get from the other GM to the output voltage. We can just add a factor of 2 here. Guys, that the output voltage noise at a delta omega offset is going to be 4 kT into 1 by delta omega C whole square multiplied by 1 by RP plus gamma GM0 by 2. You also know that for steady state oscillation, this 2 by GM should be equal to RP. So that was the analysis we have already done earlier. So by this minus 2 by GM was equal to this negative resistance, which has to completely compensate this effective parallel resistance RP. We know that in steady state, 2 by GM0 is equal to RP. It implies the output noise PSD is going to be equal to 4 kT 1 by 4 delta omega square C square into 1 by RP 1 plus gamma. And if gamma is almost 1, then we can say that the noise contribution due to the RP is equal to the noise contribution due to this transconductor. And this is mainly true when we are at far off offset, where only the thermal noise is being considered. We are ignoring the effect of flicker noise. So one point to note here is for gamma approximately 1, phase noise contribution from cross coupled here is the same as that from C loss. And this is mainly true at higher offsets where flicker noise doesn't come into picture. And of where thermal noise is dominating. Coupled noise is same as the tank noise at far off offset. So now let us try to rewrite this output voltage noise in terms of the Q of the tank. Here we can see that this will become KT 1 plus gamma. Then we have got 1 by delta omega square C square RP KT 1 plus gamma. We know that the Q tank is equal to omega naught C RP. So the C square we can write as Q square by omega naught square RP square into 1 by RP is equal to KT 1 plus gamma RP by Q square omega naught by delta omega whole square. So this expression is the output voltage noise. This is not the phase noise. To find the phase noise, we need to just normalize this voltage noise with the carrier power or the LO power. So the phase noise at delta omega offset S by delta omega is going to be half of this output voltage noise, because only half of this output voltage noise contributes to the phase noise, while the other half will contribute to the amplitude noise. This is assuming equipartition theorem is applicable. We have so the output voltage noise PSD divided by the carrier power, which is the output amplitude square by lies the phase noise at delta omega offset is going to be half of KT 1 plus gamma RP by Q square omega naught by delta omega whole square into 1 by the carrier power. Now, few points to note here. The moment the tank and its loss is fixed, then automatically the contribution from the cross-coupled pair is also fixed, and it will only scale by this factor of gamma. So what we have in our hand is RP, the Q of the tank, and the carrier power or the oscillator output amplitude. So when we are trying to optimize the phase noise of the VCO at far off offset, the far off phase noise, if you are trying to optimize, then we can see that we can try to maximize this output voltage swing as much as possible, but there is going to be a limit. That limit is determined by the breakdown of those transistors which are present, and in some way it will be related to the supply voltage. We want to maximize this output voltage amplitude, and we know that to be maximized, but it is limited by breakdown. We also know that this output amplitude is dependent on the tail current which is used to bias the VCO, and this differential amplitude at the output is equal to 2 pi I naught into Rp. If the maximum value of this amplitude is fixed by the breakdown, then automatically this product also gets fixed. Product is fixed for maximum Vamp. So if we are given some power budget for this current, then accordingly we have to choose the Rp so that this product is giving us the maximum amplitude which is possible. Another way to look into this optimization is that if this Vm is fixed and we are ensuring that we are always operating at the maximum amplitude, then in such a scenario, we need to go for as low Rp as possible for a given Q of the tank to get the low phase noise. So when we go for a low Rp, automatically this current consumption in the VCO is going to increase so as to keep this product constant. So that is a standard power noise trade-off. So if you want to reduce the phase noise, we have to burn more power. Then choose maximum Q possible for the inductor, because the inductor Q is going to dominate the Q of the overall tank, especially when we are talking about few gigahertz frequency of operation. And Q will decide tank Q. And for the maximum allowed output amplitude possible, we can choose a low value of Rp so as to meet the phase noise specification. Then choose Rp. Since we have already fixed the Q, effectively we are also going to choose the inductor when we choose the Rp to meet the PN spec while getting I naught accordingly to keep Vm to its maximum value. First, we will try to find what is the maximum Vm possible. We are also going to find what is the maximum Q possible in the process for the inductor. Then we can choose the inductor such that it has the Rp which is required to meet the phase noise spec. And once we know the Rp, then we need to scale the I naught accordingly so as to maintain this product constant. This kind of optimization we can use for far off phase noise, as the phase noise is mainly dominated by the thermal noise of the tank and the cross-coupled pair. Here few points to note. This tail current source can also contribute to the far off phase noise because of mixing action which is present in this circuit. So we can see that if there is a noise present at this I0, then looking from this noise source side, it will appear as if we have got two switches which are operating at this LO frequency, just like the case we saw in active mixer. So in such a scenario, the noise from this tail current source, especially around 2 omega naught, will be multiplied with the fundamental frequency of this LO signal, and 2 omega naught multiplying with omega naught will contribute to some component at the omega naught. So as a result of which, we are going to get some output voltage noise because of this tail current source, resulting in the output phase noise. And not only this I0, in the entire common mode path, if at all there is any noise present around 2 omega naught, that noise is going to appear at the output because of this mixer action of these two transconductors. So many times people try to add a filter at 2 omega naught in the common mode path to reject this noise around 2 omega naught. So the contribution from the common mode path at this 2 omega naught will not appear at the output. So the tail current source noise at 2 omega naught can appear at the VCO output due to mixing action of the cross-coupled pair. So many times filter at 2 omega naught is added in the common mode path of VCO. So when we are implementing this VCO circuit on chip, we need to also take care of the process variation, the voltage supply variation, the temperature variation, which is going to be present in all the real applications. So under all these variations, the frequency of this VCO will not stay constant. So we might design the VCO for, let's say, 1 gigahertz, but because it's PVT variation, the frequency can be anywhere from 900 megahertz to 1.1 gigahertz. Such kind of variations, of course, are not desirable. And we can also see that while the VCO is operating, during the operation itself, due to the variation in the supply and temperature, the frequency can vary at any time. So this PVT, which is process voltage temperature, variations is VCO frequency to deviate desired value. So if we are operating in a specific frequency band where we are trying to transmit or receive in a specific channel, then the frequency of the LO has to be very precise. So we can't allow these PVT variations to cause such high deviations in the VCO frequency output. So to keep this VCO frequency tightly controlled to the required value, So let's say this is your VCO output. Then in such a scenario, we need to use a feedback system, and that feedback will require a tightly controlled, well-defined, stable oscillator. And using that stable oscillator, we are going to ensure that the output of the VCO frequency is also very well defined. So this is a simple model for the VCO. Now, just running this VCO in this open loop is going to suffer from this PVT variations. So generally, what we do is we take a feedback. Let's say there is a feedback factor of 1 by n. And after this feedback, we compare this feedback frequency with a stable frequency. Let's call it a reference frequency. And just like in any other feedback system, we add a lot of gain in the forward path to make sure the output frequency is tightly defined by the input reference frequency. Now in this setup, we can see that this FVCO is going to be equal to n times the reference frequency, and this reference frequency is generated by a stable oscillator. Many times it's a crystal based oscillator where a quartz crystal is used to define the oscillation frequency. It's a negative feedback system. And here we can see that in a way this stable frequency of the reference oscillator is multiplied by some integer value to generate an output frequency. So this kind of setup you can also call as a frequency multiplier. But in general, these feedback systems used to generate well-defined frequency at the output of the VCO is called as frequency synthesizer. Generates tightly controlled LO signal using VCO in a negative feedback. As we have seen that not only this frequency, even the phase of this output frequency is very important for the application. So we create this negative feedback such that the output phase of the VCO is also tightly controlled by the input phase of the reference oscillator. So such negative feedback loops are called as phase locked loop or PLL. Every transceiver will be having PLL to generate the stable LO frequencies. And if the transceiver is operating in the FDD mode where the transmitter and receiver both have different LO frequency, then we can also expect separate frequency synthesizer, which in turn will be implementing using a PLL for the transmitter as well as receiver. So in addition to this PLL being present on chip, you'll find that the VCO output may not be able to directly drive the mixer. So there will be LO buffers which will be placed between the VCO and the mixer to take the LO signal and drive the mixers. So LO buffers used to take VCO output and drive mixer switches.